Okay. I thought I might try to speedrun guard statements, just like Swift, or like Rust's let else. I like the idea of let else because it doesn't add any new keywords, but we can't really do let else because our matching actually goes left to right. So, and in K1 we can say if foo is pattern and then bindings, and that works like a normal if else. Whereas Rust would be let sum x equal foo else. I mean, we could do it, but it makes no sense because we match left to right. So, which is nice because then if it turns to a switch, nothing moves around, right? Let's just become switch foo, and then cases. So for now, we'll do guard. I don't like adding a new keyword, but it's not very fast speedrun if we belabor all the details. So let's see what we can do. Semantics are pretty simple. It's like an if not, and the block you give it, you have to give it a block, and it has to terminate. So when we do just the print line, it should fail, and then you can also do any Boolean. So let's get to it. The first thing is, I guess, we need an entirely new keyword, huh? See, I don't love it. I don't love it. Let's just search for keyword constant everywhere. We're gonna add guard. Okay. And is keyword, yeah. All right, so there we go. And if we can just, is that what that is? Go ahead and run the tests. Fail. Ah, yeah, because of that. Now if we run the tests. They're slow because I'm recording. Now they're actually running. That was all compiling. All right, so let's parse this thing. So this is a whole new type of statement. We have use, we have let, so let's put it right after let. Yeah, see, I'm already not liking having an entirely new concept versus it just being a type of let. But I just don't know how. So really we're let x. X is what we're binding, and it's equal to what's inside foo. Right, it'd be great if that's just how you bound things. Because once we add destructuring, what's nice about destructuring is that it still goes there. But once we add guards, so we could do, I mean, we can make it a guard let, but it doesn't even have an equals in it, so it doesn't look anything like a let. Let guard. Well, I told myself I wouldn't worry about it. But now I have to actually write the code. It feels bad. Let's just parse guard. I think it adds a lot of value. Okay, so we'll just go wherever parse let is. It used to be called a valdef. We'll parse guard down here. I can do a lot of parser code in these videos because I'm always trying to like add a feature from scratch. So we have keyword, we have one pattern, and you are allowed, so we'll do a chain of patterns. So we'll all say any expression here, and we'll treat it exactly the same as a matching if, because this would let me to say, let me say, or not live, or live equal true. No, and if it's an and, then the binding counts. If this was or, then it still works, but it would say, hey, you can't bind anything. But this would be valid. If it was some or live is true. So let's leave in a more advanced example. With the or, which is going to be underscore, and then you should be able to bind with and live. So Copilot. All right. Patterns. So let's go to parse is. Pattern. Keyword is pattern. So we're saying any pattern. Is does a single pattern, but not matching if. Sorry, if expr. And the consequent can just be any expression. Okay. So I think that's how we're going to do it. Right, that doesn't exist yet. So just looking back again. Yeah, so actually just an expression here. I wanted to say a pattern, but we're just going to parse expression and let parse expression handle that this is an and. So it's going to parse like this. As an and with an is expression on the left. So this is just going to be our kind of our condition. Yeah, it's our guard condition. It's our condition expr. And then we'll have yeah. Just consume an else directly, and then we need a block. Now the question is, do we allow you have to call crash. Yeah, not a block, any expression here. So we want this to work as well. And that's kind of cool. Body. Else body. Expression. And let's just make up parsed guard. So it definitely has a span, which will get to. We have our else body, which is required. We have our condition expr. And I think that's it. The span is going to be extend expr span is the one I want from the end of the else body. You know, I'm just going to go extend to here from the keyword span. And that's not parsed guard, so we're going to go parsed statement. And we have guard. Oh. And we'll document it. That's it. There's our parsed guard. And a lot of things are going to complain because we now have a new type of statement. We'll call it G. It does need a span. We'll jump on down. What's the matter with you? Sure. This is super unfinished, but we'll just go ahead and do our part to do guard. Oh yeah, I don't really print the AST very much. I print the typed one. I either print what the user typed, the raw source, or the typed AST. And this is our untyped AST, our actual AST. Yeah, I could go ahead and for a demonstration. So this is going to be display expr ID. We would just display the condition, and then we would just write view else. What's wrong with you, right? We need a writer. What's the matter with you? Are we happy now? No. You want that at the end. Need to flip all those around. And just display the else body. So now at least one of those is complete. And let's see, and we go into our type checker and we need to implement evaluate statement. So here's let's, here's assignments, which are kind of like let's. So I'll go down, and set ref. No, it's more like this one. Oh, that's interesting. Starting the size here. Oh, before the clone, yeah. I might go ahead and do the same if we're going to be cloning it. And I think it is going to be 12 as well. Yeah. 12 bytes. And what do we want to do? Well, we want to evaluate the pattern. So we're doing, what does this desugar to? This desugars to well, it could be an if. Yeah, so I think it should desugar to a let. A series of lets for the bindings. And then the obvious desugaring is an if else, but then the entire rest of the function, you know, everything becomes nested inside if else's when we have early returns. Or yeah, I just would prefer a flatter structure because then we're going to end up with a flatter structure in CodeGen as well. So what it will desugar to is something like for the one starting on line 3, it would be like let x, which can just be undefined, right? Because we can write illegal code here, and then this would be, you know, we have the pattern. So if foo is dot sum, you know, if matches, something like this. So however we do conditions, right? And then if, well, not matches x equal foo dot unwrap, right? Else crash with and then that's kind of where we are, and then from here we know x has a value. The problem is that this is more than yeah, so the other obvious one is to just run the rest of the function inside an if. Oh, I'm still on the wrong branch. So I don't actually have a way to do this without an initializer. So in practice, what I would do is probably yeah, this is actually really interesting. I'm not sure that this lowers very nicely into my main typed IR. I lower way more complex things than this because I do these matching ifs with multiple arms and multiple bindings and Boolean expressions. And like, and this is a test that it doesn't compile because of the or. You know, this compiles and works, but what I could do is I could introduce a new node to the typed IR called a guard, and then that lowers really easily, and then all the work is in CodeGen, and it's kind of straightforward. It's kind of straightforward from there. So what I would generate ultimately, let's do the matching if. So when I eval matching condition, yeah, while loops can also match. Well, that's cool. Forgot I did that. So yeah, so if can do pattern matching. So what it produces is these. Well, no, if we go down to all the way what we send to CodeGen is a match expression. With a series of initial let statements and then arms, where each arm has setup statements that you run if you get to that arm, an actual condition, and the condition runs before the bindings, then the bindings are created, and then the guard condition gets to use the bindings. And then if the guard condition is true, the pattern condition was true, then it runs the consequent expression. So could I lower guards to this structure? I definitely could, but it's not that nice. Because the whole rest of the function still ends up in like a different block when, you know, the LLVM that we would really like to generate for this is going to be something like, you know, we get to this guard, we have the condition, let's say it's just conned, whatever. We want to BR conned, it's con BR or whatever. To, you know, guard else. I guess. And then just continue the block, right? Guard else is down here, and it has our crash. Right. And then we just continue. Yeah. Yeah, I think you want to do something first class, which is unfortunate. So typed statement is another beast. We have 3. So we would add a guard here. Yeah. No, it is a type of statement. Right. It's not an expression. So expressing it like a match is just kind of odd anyway. More like a let. So if we did make a guard, then we would want to say, you know, in CodeGen speak, we would have an initial binding for our match targets. So, you know, this would be like initial statements. Setup statements. Yeah, sorry. Let me get the way a match arm has patterns. Multiple patterns does that mean the user? It means this was an if statement. In our case, you Could have multiple patterns. The patterns, oh, we don't really need them. The patterns kind of get compiled away. So TBD if we would keep those. Those are just for our analysis. CodeGen doesn't, yeah, we get patterns. The patterns are encoded and it's actually exactly this. Probably unnecessary. Some statements. Those statements are going to be things like this. The reason we do that is so that we don't run the target expression, many times. So we would need set of statement, pattern condition, obviously, the binding statements. There is no single guard condition because we could do also or. Something. And how does a matching if compile down? If I have. Oh, it goes into the condition. Yeah, those things become part of the pattern condition, right? Let me go back to the matching if. It's a Boolean chain. So when it's an is, that's fine, and when it's a binary op, we recurse. Yep, we check if it's an or, and then we push to conditions. So handle matching if rec. All bindings. Patterns combine with and we reduce. Yes, okay, we reduce all of the conditions, and then the combined condition isn't a matching condition. All right, which is like an inner type. So we want exactly one of these with binding eligible and everything. So we actually, I think we exactly want eval matching condition, which is kind of crazy. And then all we would do is, instead of putting that inside a match for CodeGen, okay, no. Could we do it like an if with no else? How do I compile if with no else's? we always return a phi value. So yeah, ifs with no else's also result in like more blocks than they kind of need to, because we don't differentiate. By the time we get down here, we treat them all the same. Because I was trying to make CodeGen as simple as possible so that I could actually get it to work. But yeah. So we could totally compile it to an if else, but oh no, because we need, that's right, we need to create bindings. So we need to we could just compile it to multiple statements. So nowhere, right? So like eval statement returns one statement. It would be really useful in some places to be able to produce like two typed statements for one parse statement. And if we could do that, then I think that we could compile this to, we get our matching condition. So then we would just produce a few statements. We would produce the set of statements. We would produce the combined condition. And interestingly here, can, oh shit. So, can I use X here? Because if I can, then it works more like a guard condition. And then what establishes that ordering, right? Is that a left or right thing? Because I do know which parts of this chain are patterns and which ones aren't. So I could run them first. Create a block, add their bindings, and then run them here. or we could say that the bindings aren't available outside. Which is why Swift does it with a comma, because it's an after. Well, I gotta go to bed, but tonight I learned that we're not quite ready for this construct. At least it's not, well, not that we're not ready, but this is a more interesting, complicated, not even complicated. Yeah, if I want to support all the Boolean expressions attached, this compiles to something quite a bit more complex than I thought it would compile to. Because I thought I already had everything to do it with that matching condition function, because it's the exact same as this thing we already support. The problem is I don't want to put, the entire rest of the function inside a block. I don't know why, just aesthetically I don't. But if I did, we're done. I don't even have something that does that. Like, it's just assumed that we generate statements one for one with parsed statements. There's no way to move the control flow such that like we're now writing into a previous expression or statement. Oh, very interesting. Well, thanks for watching.